Hello everyone, welcome to Dakshina e-classroom program. So up to last lecture we discussed a little bit about fluid. We saw what is the definition of fluid, what we exactly mean fluid, and fluid basically comes liquid and gases, the properties of fluid, density, variation, density of mixture, pressure, then why fluid apply pressure, how it applies, some properties of fluid related to pressure, and then pressure variation in fluid, pressure variation in accelerated fluid means one container is accelerating, and then we talked about Pascal's law and some pressure measuring devices, that is manometer and barometer, and we discussed about Archimedes principle. So Archimedes principle says that if an object is submerged partially or completely in a fluid, then it is buoyed up by the fluid, means fluid apply a upward force, we call that buoyancy force on the object, is it, and that force is equal to the weight of displaced liquid. So means if a container is there and some object is submerged either completely or partially, then when object is going inside the fluid, it will be displacing some liquid from like the space it is going to occupy or it is occupying. So the force applied by the fluid will be equal to weight of that displaced liquid. We saw that in the last lecture. Let's continue from here onward, and the next comes is law of flotation. So first thing is, from Archimedes principle we can say if an object, is it, of let's say density rho and volume v is submerged in liquid of density sigma, is it, and let vi is the volume submerged of object immersed. So means this is a container filled with some liquid of density sigma, and we have one object, right, like this, its density is rho, and this is submerged up to here, so that this is the Vi is the immersed volume, and total volume of this liquid or this solid body is, let's say, V. Then buoyancy force applied by the liquid, we can write it Vi into sigma into G. This is what we have seen up to here, right? And the weight of the body will be equal to what? V into rho into G. Volume, total volume multiplied by density, mass into G is a weight. So now law of flotation, it's simple thing, like you can even design by yourself. What I mean, like it's telling you the condition that when an object will float, when it will not float. So what is the condition for floating? You can say right now on this object forces acting is, one is its weight downward, is it, another force acting on this object is its buoyancy force. So what can be the possible situation when the body will be floating? If this weight downward force is balanced by this buoyancy force, then only it will be able to float. If this is heavier, this buoyancy force is not sufficient, it will simply sink, right? So that is a condition. So law of flotation, we can say if you can write the buoyancy force is greater than or equal to weight of body, object will float, right? Simple condition. So here you can write F buoyancy is greater than, it can be greater than equal to weight of body, right? This implies Vi into sigma into G must be greater than equal to what? V into rho into G. G can be cancelled. This implies 1 second, because buoyancy force. All right, so we can write it should be maximum, like it can be equal, is it? So because we need just like the weight should be balanced, or this condition also. So okay, let's say up to here, then this implies Vi into sigma must be greater than V into rho and greater than equal to, this implies sigma I can write upon rho greater than equal to V upon Vi, is it? We can get one condition here. Okay, so we got it, this condition, and the like I just need to like modify a little bit, because we want the object to be simply staying in equilibrium. We don't want it to be pushed out actually, so that's why the forces must be balanced, not like imbalanced, is it? So in this is the weight, this is the buoyancy force. So here you can write, it will be better if we write buoyancy force is balanced by the weight, or weight is like both the forces are balancing. So this is the condition we are getting, and now this implies I can also write it rho upon sigma equal to Vi by V. Okay, now one more condition about this Vi by V. If we want the object to be floating, then what should be the condition, is it? For object to float, right? What should be condition? We can say Vi by V, this should be what, less than equal to 1, because maximum volume of the object which can submerge will be equal to simply total volume of the object, is it? This is the immersed volume. So this always like in other case for floating condition, the submerged volume or immersed volume of the object must be less than its total volume. So this condition we can always write, right? So this implies Vi must be always less than equal to V, or Vi by V must be less than equal to 1. This implies I can write rho by sigma must be less than equal to what? 1. And this implies rho must be less than equal to sigma. So this is the condition in terms of density of object and density of liquid. So when an object will float, if density of object is less than density of liquid, object will definitely float, is it? So from here we can write, if rho is less than sigma, object will float with Vi less than V, means some partial, some volume submerged. And here you can write second, if rho is equal to sigma, what will happen actually? Object still float with Vi equal to V, means complete object will be submerged and it will be floating. That will be like, so it will be float with completely submerged situation. And third condition, if rho is greater than sigma, in that situation it is not possible for buoyancy force to balance the weight, so object will sink. So the condition is not anything like complex, not difficult. Simple terms, we understood this is a liquid of density sigma, object density rho, let's say total volume is V, and I'm assuming Vi is the immersed volume of the object. Then we know the buoyancy force from Archimedes principle acting on the object is this, weight of the object is this, and for object to float its weight must be balanced, is it? Or buoyancy force should be like I would write, it should be equal to weight of the body and object will float, is it? Body, object will, then object or body will float. So this is equal, then we can write this is the condition. And another comes condition for this, for object to float, the immersed volume must be less than equal to its total volume. So from here we got this condition, then we got the relation in terms of density, and from here we can write these conclusions that if density of object is less than density of liquid, it will float with some partial volume or some part of the volume immersed. If both our densities are equal, it will still float with complete volume is immersed in the liquid. And if density of object is greater than density of liquid, then it will definitely sink. There is no possibility of floating in this situation. Clear? So okay, so now we understood actually, and let me just tell you one case. Like here V is the total volume of the object, density is rho, and density of the liquid is sigma, and Vi is the volume of the object immersed. Then sometime like you are asked to find or calculate the fraction of object submerged, fraction of object is outside, is it outside or inside? So here we understood already object is floating, is it is floating, means definitely rho is greater than rho is less than sigma. This condition is already there. So F buoyancy force is balancing weight, and here you can write Vi into sigma into G is equal to V into rho into G. That is the condition. Now we are asked to find fraction of volume submerged. Is it fraction of volume of object submerged, is it? So that we can calculate. This is what volume submerged, this is total volume. So that easily we can get from there Vi rho sigma into G is equal to V into rho into G, and this implies Vi by V is that fraction submerged, and that comes out to be G gets cancelled. This is equal to rho by sigma. This will be the volume of object which is submerged, or fraction of volume outside, fraction of volume of object floating outside. That will be equal to what? Total volume means 1 minus this fraction, that will be equal to fraction outside, that 1 minus F submerged, and that you can write basically V minus Vi by V, and that can be also written as sigma minus rho divided by sigma. So that is simple. Like if this is the submerged fraction, then submerged fraction plus outside fraction total will be 1. So 1 minus of this will be the outside fraction. So means like if problems are asked about something related to this, then you can easily answer. Let me give you just one simple example. So we know the density of ice is 0.9 gram per cc, and density of water is how much? Density of water is 1 gram per cc. So now you are asked to find the fraction of ice submerged in water. So that is like simple application. So we can easily ask, so fraction of submerged, that will be equal to what? Vi by V, that is equal to what? It is equal to density, that is rho divided by sigma. Clear? And this is equal to 0.9 divided by 1, that is equal to 0.9. So this is the fraction of the ice. So 0.9 fraction will be submerged, only 0.1 fraction will be staying outside, right? So similar situation, like depending on if density of two substance, object and liquid is given to you, you can calculate how much fraction will be submerged, how much fraction will be staying outside. So this is all about law of flotation, that comes basically from Archimedes principle. And when object is floating, then definitely it's what? It's in basically stationary equilibrium or translational equilibrium, because net force acting on the body will be balanced and will be equal to 0. And here comes one more point, that is about rotational equilibrium. So let me tell you the condition for that. Okay, so for talking about the rotational equilibrium of floating bodies, we need to define few terms first. So first is center of buoyancy. So what is that actually? Just imagine this condition: object floating with this much volume is like submerged inside the liquid. This is liquid, density is sigma, density of object is rho, and total volume is v. Then what is center of buoyancy? Center of buoyancy is basically the point on the object where total buoyancy force is assumed to be acting. Is it the point about which total buoyancy force is assumed to be acting? Or in simple term, that actually is equal to center of mass of submerged part of body, or it is equal to center of mass of submerged part of a body. So means like, just forget about this upper part. Where will be the center of mass of this body? It will be somewhere here. So this is the center of buoyancy and B, right? I hope it's clear. Or where we can say the total buoyancy force is acting. It is that point where we can say, we can assume the total buoyancy force is acting above this point, and mathematically that comes out to be equal to the center of mass of the submerged part of the body. So let's suppose this object is floating in this situation, and in this I will write this is the center of buoyancy where like net buoyancy force is acting. Clear? Similarly, I can write next is center of gravity. Center of gravity. So where like you can say total weight of body is acting, means gravitational force, and that it is it coincide with the center of mass of body. In normal case it always coincide. Okay, so simply like in this situation, center of mass of this body will be somewhere here, and this is denoted by G letter. Center of gravity we denote G, center of buoyancy by letter B, right? Now this is the condition. Another thing, if I am disturbing this body, let's suppose it is tilted or pressed little bit, then what will happen? Like submerged part of the body will change, definitely. So because of that, your buoyancy or center of buoyancy can change. Do you think like center of gravity will change also? No, center of gravity will not change. So it can change if like body is disturbed, it can change, right? But it's fixed. It is fixed for a body, right? So then I need to, that there comes one more point, that is called, third is called meta center. Let me draw the diagram, then I will tell you exactly what is that meta center. Okay, I need to define here one more, and that is called meta center. It's you may find it a little bit different, so just pay attention and I will try to explain you like clearly. First thing is like center of buoyancy. I hope you are clear with this point. It's center of buoyancy, mathematically it's equal to center of mass of the submerged part of the body. Center of gravity, it's simply equal to center of mass of total body where total weight is assumed to be acting. And if I'm tilting it, I'm disturbing it, I'm pressing it further down, then what will happen? This part of the volume, part of the object which is submerged will change, and definitely your buoyancy will change. But because center of mass of the complete body will still remain same, so that's why G will not change. Now look at this situation. So this is the same body. Let's say I have just drawn a different diagram. Now in this situation, so when it was initially lying, staying simply in a equilibrium position, floating, so let's say this is the G, center of gravity, and B is the center of buoyancy. What I did is I just pressed it down and I tilted it. So then different possibilities can be there. The center of gravity will be still staying there. This will be your center of gravity, but center of buoyancy, there is possibility. Just don't go for the exactly to the mark and to the scale diagram. I am just talking about the different possibilities, and just pay attention on the concept. Okay, so the point is that because now I have changed this here I have changed the amount of volume or submerged volume of the body. So that's why there is two possibility, that center of buoyancy may be lying, let's say here, or maybe lying here, let's say here. Okay, so just for a moment I am considering center of buoyancy. Now this is the volume of the body which is submerged. So for this it will be lying here somewhere, but let me consider it just lying here. So in this situation, if I draw this dash red line is original, that line that was actually vertical. So this is G and this will be like your B, is it? But now because body has tilted, so now if I look for new center of buoyancy, so let's say this is your new B prime, center of buoyancy, center of buoyancy. Okay, now if I draw a line, vertical line passing through this point, so vertical line, let me draw it with the scale, is it? So if I draw a vertical line now passing from here, okay, so vertical line passing from this center of buoyancy, let's say this is the vertical line, it will be definitely crossing the earlier vertical line at some point, and this point of intersection is called meta center. Let me repeat it. First thing is, originally body is floating. For that I marked G, center of gravity, and for the submerged part, when it was simply floating by itself, I marked center of buoyancy, that is B. I draw a line passing through these two G and B point, and this is that vertical line marked with black. Okay, now if I am tilting it, this black line will also tilt exactly. Let's suppose I have drawn it. So this now dashed red line is actually the earlier black line, is it? What will happen, because now I have disturbed it, so center of buoyancy B prime will change, but G will still remain same. Now in this disturbed position, red colored body, I draw a vertical line passing through this new center of buoyancy. Then definitely this vertical line will cross the earlier red line drawn, is it, through which G and B is passing, and it will these two lines will cross intersect at point, and that point is called meta centers, is it? So meta center I can write it is, if in simple terms I am writing, it is the point of intersection of a vertical line drawn through center of buoyancy of disturbed position of body and a vertical line passing through center of buoyancy and center of gravity in floating equilibrium position. So the intersection of these two lines will be the point that is called meta center. Why it is important, that I will also tell you. Let me write the definition first. Okay, so meta center, it is defined, it is the point of intersection of a vertical line passing through G and B in floating equilibrium position, and a vertical line drawn through a point B prime. It's actually B prime, that is center of buoyancy in displaced or disturbed position. So this red line is that line passing through, this is, you can write G, and this is B. So one line passing through GB, and another line is in disturbed condition. There will be new center of buoyancy, a line, vertical line drawn passing through new center of buoyancy. So these two line will intersect at a point, and that point is termed as meta center. Now why it is important, actually how it is important, with the help of this meta center we can define whether the equilibrium of a body will be stable, unstable or neutral. And let me tell you how we can define that, how we can say that based on meta center the equilibrium will be stable, unstable or neutral. So just I am here considering different like conditions. Let's say this is a G, and for this position, this object, if I disturb it, let me draw the diagram first. Okay, so this is the diagram. Here I have drawn this initially black diagram, that is the initial equilibrium condition, and let's say this is the G, center of gravity. Now I disturb the body and center of buoyancy B prime is here. Now this is G, center of gravity, and let's say meta center is lying above center of gravity in this situation. So let me tell you, equilibrium, you must be already the like basic meaning, what is the stable equilibrium, unstable equilibrium, neutral equilibrium. Neutral equilibrium means, let's say one body is in equilibrium means no net force, no net torque. If you disturb it, if it is simply staying there, that is called neutral equilibrium, means it's not like getting disturbed. It's always in equilibrium, and wherever the position, wherever the condition, orientation you want to keep it, you will keep it, it will be simply staying in that's orientation. That is your neutral equilibrium. Another comes is stable equilibrium. Stable equilibrium means if you disturb it, the body has tendency to restore or come back to its original or equilibrium position. Is it? Let's suppose if it is like this, so it is in equilibrium position. Now what will happen actually if I disturb it like this? Is it? I disturb it, and if I release, if it is in back tendency, it has tendency to come back to its original position, it will be in stable equilibrium, right? Now if just I hold it like here, is it, and if little bit, if I disturb it little bit, it will fall down actually. So you can just imagine if it is holding here, right? The situation here is also just similar. Try to understand it. Here I am holding it here, center of gravity, center of, like, now what will happen actually here? So if I just disturb it little bit, it will simply fall, means there is no possibility of coming. If I am disturbing it, there is no possibility of coming back to original orientation. But if this is the situation, if I am holding it here and if I am disturbing it little bit, there is tendency that it will come back. If I am disturbing it, it will come back. If I am disturbing it, it will come back. So this is stable equilibrium, means when you are disturbing it, if body has tendency to come back to that orientation, that is a stable equilibrium. If it is disturbed and it's going further away from that equilibrium position, it will be unstable equilibrium position. So with the help of this meta center, we can comment very easily that equilibrium will be stable, unstable or neutral. So the condition is that if meta center is lying above G, center of gravity, body will be in stable equilibrium. If meta center lies below center of gravity, the body will be in unstable equilibrium. If both of these coincide, the body will be in neutral equilibrium. So first is stable equilibrium. The condition is that if meta center of body lies above center of gravity, the equilibrium will be a stable equilibrium. Now you need to understand also it why. Okay, so let me explain you. Just pay attention, listen it properly. Now forget about this black diagram, just focus on the red diagram. Now see it whether this body has any tendency to come back to original orientation or not. If it is having, means it's belonging to stable equilibrium. And I told metacenter of body lies above center of gravity. In this situation I have considered exactly that. Okay, so now first thing is, on this body what are the two forces acting? One is buoyancy force, another is gravity force. Is it? Means its weight. So now just focus on this metacenter. This buoyancy force, it's simply passing through that. So what will happen actually? It will simply like balance the weight, but do you think this buoyancy force will apply any torque or trying to restore its position back to original position? I think it's not, because if you just look at torque of this buoyancy force about this, it will be simply buoyancy force and then perpendicular distance is 0, so torque of buoyancy force is 0. But now see, torque of this mg will be acting downward. So you can see mg into this perpendicular distance. So this mg, can you just imagine if you just calculate the torque about metacenter, and mg will try to bring it back to same position, it's trying to disturb it. You can see the torque of this will be in this way. Is it? Tendency of the torque by weight about metacenter will try to restore it. If you just look at it, then this is the R cross F, so it's basically trying to rotate it, trying to bring it back to original equilibrium position. So that's why this is a conditioned situation of stable equilibrium. Let me show you with the same diagram by drawing a diagram that if metacenter is lying just below the center of gravity, then how this will play exactly opposite role and it will try to disturb it further. Okay, so now look at this diagram, lower diagram here. My container, fluid, object, floating, center of gravity, buoyancy will be lying somewhere here. This is the vertical line. I disturb it, this vertical line now become this. Center of buoyancy changes to here, this is your B prime. I draw one line, vertical line passing through B prime. This is vertical line. Okay, so I can mark this is original vertical line. Now this dash 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 is changed vertical line that is passing through B prime. So this is intersecting the original line here, and this is your meta center. Now you see meta center is lying just below the center of gravity. Now see, so again now look at meta center. So calculate the torque about meta center, because meta center means no force is like meta center is not some force actually, it's just one point, is it? But it help you in identifying the equilibrium whether it's stable or unstable. So for that, so now metacenter is this point. So it's basically it's telling you that point, that about which point you should be thinking, you should be looking for checking the equilibrium of body, so that you don't have to think about that. It's giving you directly the point that look for metacenter. So this is the point. So just consider here metacenter. So I am talking about now this. Force or torque due to buoyancy force B prime will be simply passing through it, so it's not doing anything. Now I have disturbed from this like it was originally in this orientation, now it has been disturbed to this orientation. So now this is disturbed to, now see, due to this mg, its torque about this metacenter, it will try to rotate it this way or it will try to restore. You can easily identify in this situation the torque about basically torque of weight about metacenter, it's trying to rotate it in this direction. So it will, once you are releasing it, it will fall down, it will completely like move away from its equilibrium position, and in this situation this will be the condition for unstable equilibrium. So I hope you must be clear. First I defined center of buoyancy, center of gravity, then center of buoyancy for disturbed position. A line passing through original center of buoyancy and center of gravity is one vertical line. Disturbed, new center of buoyancy, a vertical line passing through disturbed center of buoyancy, crossing the earlier line. The point of intersection is metacenter. About metacenter, we will calculate torque. If the body is disturbed and torque about metacenter is restoring, it's trying to restore, trying to bring the body back to its equilibrium position, that means it will be a stable equilibrium. it is disturbed from here, and now you can see if you just calculate the torque of weight about this point, it will disturb it further, it will try to disturb it further, is it is trying to disturb it further. So this is your unstable equilibrium. If both the points lying exactly at same point coinciding, wherever you are releasing, the body will simply stay in that position, that will be your neutral equilibrium. So this is the condition of stable equilibrium. Let me write the condition for unstable and neutral equilibrium also. Okay, so this is the condition, stable equilibrium in this situation when metacenter lie above the center of gravity, that will be the condition for stable equilibrium. If metacenter of the body lies below the center of gravity, like this situation, the body or the equilibrium will be unstable, and if metacenter and center of gravity both coincide, the equilibrium of body will be neutral equilibrium. So this is all about type of equilibrium, law of floating, Archimedes principles. I hope everything should be clear up to here. On this topic, some logical questions are asked, or otherwise you will be asked if metacenter, or some statement type of questions, if metacenter of the body is lying above center of gravity, the equilibrium will be stable, equilibrium will be unstable, which is the correct statement, right statement, wrong statement, something like that. So if you're just remembering the things little bit and logic, I think you should be like easily, you should be in position to answer such questions very easily. So this is all about basically your Archimedes principle. Let's see next. Okay, so see one problem based on it, based on Archimedes principle. A concrete sphere of radius r, capital R, has a cavity of radius small r. So we are having one concrete sphere of radius capital R, and it is having a cavity. So this is concrete, right? And radius is this capital R, but there is one cavity. This is cavity of radius, this is small r, and this cavity is filled with sawdust. Okay, means like it's a light, basically dust, and we want this sphere completely. So now concrete, the specific gravity of concrete and sawdust, this is concrete and sawdust respectively given. For this sphere to float with entire volume submerged, so we want this sphere to be floating with its entire volume submerged underwater. Ratio of mass of concrete to mass of sawdust is, so this is the problem. I hope you are clear with it. So now we are asked to find the mass of concrete to the ratio of mass of concrete to mass of sawdust, because you can see if there was no cavity, then the specific gravity of concrete is like 2.4, it's 2.4 times density of water. So that is like no possibility of the possibility is there for this sphere to float. Actually it will simply sink, but because cavity is there, that too filled with very light material, so that's why there is possibility if total thrust force acting on this sphere is equal to the weight of total weight of this sphere, it will be floating, right? That's the condition we can apply here. So here the condition is sphere must float with entire volume submerged. So first thing is radius of total sphere is capital R, cavity is small r. So what is the volume of concrete? V concrete will be 4 by 3 pi capital R cube minus 4 by 3 pi small r cube. That can be written as 4 by 3 pi capital R cube minus small r cube. This is the volume of concrete. Volume of sawdust 4 by 3 pi small r cube. Total volume of sphere 4 by 3 capital R cube. Now for sphere must float, so for this implies the thrust force must be balancing what? Weight of sphere, right? And thrust force is how much? So let me say 4 by 3 pi capital R cube into density of water will be how much? 1 multiplied by G. So this is the total thrust force. That should be equal to what? 4 by 3 pi capital R cube minus small r cube. Let's say density of this is rho 1, density of sawdust is rho 2. So multiplied by rho 1 plus rho 1 into G plus 4 by 3 pi small r cube into rho 2 into g. So this is the weight of sawdust, weight of concrete, and this weight must be balanced by what? This thrust force. Cancelling 4 by 3, 4 by 3 pi, 4 by 3 pi. G, G, G. We are left with, this is r cube is equal to r cube minus small r cube multiplied by rho 1 plus small r cube multiplied by rho 2. Okay, so let me simplify it here. So then I am rearranging it. I am taking capital R cube this term this side. So it will be equal to what? Capital R cube 1 minus rho 1, and on this side it will be rho 2 minus rho 1 multiplied by small r cube. Let me rearrange it little bit. Capital R cube divided by small r cube. This can be written as rho 1 minus rho 2 divided by this will be rho 1 minus 1. Okay, but I need actually mass. So mass ratio will be like proportional to their volume ratio, because I was earlier not having the radius relation. That's why we need to get this relation. So just doing small mathematics, this is a quantity, and then I am subtracting minus 1 and minus 1 here. This is capital R cube minus small r cube divided by small r cube, rho 1 minus rho 2 minus rho 1 plus 1 divided by rho 1 minus 1. And this is coming out to be capital R cube minus small r cube divided by small r cube. This is rho 1 cancel. This is 1 minus rho 2 divided by rho 1 minus 1. And now I am doing some arrangement. 4 by 3 pi. 4 by 3 pi. So this is what? Total volume of concrete, total volume of sawdust, multiplied by density of concrete, density of sawdust, density of concrete, density of sawdust. This is equal to mass of concrete, this is mass of sawdust. So mass of concrete, mass of sawdust, this is coming out to be 1 minus rho 2 divided by rho 1 minus 1 multiplied by rho 1 by rho 2. Rho 1, rho 2 densities are given. Specific gravity 2.4 means density of concrete will be 2.4 gram per cc. Density of sawdust will be 0.3 gram per cc. Let me substitute these values. So 1 minus 0.3, this is 2.4 minus 1 into 2.4 divided by 0.3. So this is 0.7 into 2.4 divided by, this is 1.4 into 0.3. So this decimal all gone, this is also gone. This is how much? 2, 7, 2, and this is how much? 8, and this coming out to be 4. So mass of concrete by mass of sawdust is equal to 4. This is the problem, right? I hope you understood what exactly we have followed, what is the process. Just try more problems similar to this and get familiar with the concept. Let me solve few more cases. Okay, so let's see a few more cases based on Archimedes principle. First one, a cubical block is floating in liquid with half of its volume submerged in the liquid. So a cubical block is floating with V by 2 submerged. When the whole system accelerates upward with acceleration of g by 3, the fraction of volume immersed in liquid will be equal to, so initially the fraction of volume immersed is 1 by 2. So let's say once it is accelerating, then it become, let's say, Vi volume, and total volume is V. So first thing is, we know Vi divided by V is equal to what? Rho is the density of cube divided by sigma. So this is the fraction of volume immersed, and we can see fraction of volume immersed, its F is independent of acceleration. So means even when like it is accelerated by any amount, any acceleration, the fraction of volume will remain constant. So F will not change. right? So the fraction of volume, how much it is submerged, depends only on their relative densities or density of object to the density of liquid, not on the acceleration. So that's why fraction will still remain same, that is half. Okay, next question. A cube of wood supporting 200-gram mass just float in water when the mass is, okay, so let's understand the situation here. So this is the condition, and here let's say this is the cube just floating, and here this is a heavy 200-gram weight, and this is floating, this is cube. Now what is happening? Okay, just one second. So this cube is floating right now in this situation. Now what is condition given? When the mass is removed, cube rises by 1 centimeter. So let's okay, one more thing. The dimension of cube is, let's say, a. So volume will be a cube, area of the cube will be a square. Next is, when mass is removed, the cube rises by 1 centimeter. So if I am removing this mass, then cube rises by 1 centimeter upward. Is it? So what it mean? The linear dimension of cube is, that is the question, it's asking linear dimension a. But what exactly this question is saying? So what it mean? I mean, like this, how much, if a is the dimension, this rises how much? 1 centimeter. So how much volume of the cube comes out? So volume outside, now that is equal to how much? A square, area multiplied by rise, that is 1 centimeter. This is the volume. So this much volume, once the weight was placed over a 200-gram, then this complete volume, this much volume was inside. So means this 200-gram is basically balanced by the buoyancy force or weight of displaced of this much liquid. I hope you are getting it, because once this is removed, then it's coming this much outside, this much outside. Once this will be placed, again it will be coming this much down. So means this volume of this much, like a square into 1 is equal to a weight of this much volume displaced water will be equal to weight of 200 gram. So this implies I can write 200, let me write it okay, in CGS system, into G, I will cancel it. So this is the weight of 200 gram, and that is equal to what? Weight of displaced water, and weight of displaced water is equal to A square into 1 volume multiplied by density of water in gram per cc is 1 multiplied by G. This is the weight of displaced water. G cancelled out, 1 simply 1, A square is 200, solving it, A is coming out to be 10 root 2, because everything is in SI unit, so it will be in centimeter. The problem is straightforward, it's not much complex if you are understanding it. Simple thing is, this 200 gram weight, is it, when I am putting it, it's completely submerged. So means additional, like originally like this much volume was already there, but this additional, this volume was earlier outside, but now this went inside, so it's displacing additional this much water. Now you must be understanding that this displaced weight of this displaced water is balancing this much weight. So that's what exactly we applied, and we are getting it. Is it? Okay, let's see next problem here. So a ball of relative density 0.8 kg is falling from a height of 2 meters. So this is a ball of relative density 0.8, and this is falling from a height of 2 meter. This height is 2 meter. Once it is falling, how much speed it will gain there? P is equal to under root 2gh, that will be equal to under root 40 meter per second. Okay, now one more thing is, relative density of ball is 0.8, means which is less than density of water. So if it was not dropped from some height, then if it is released here, is there any possibility that ball will sink, ball will go down? Definitely not, because density of ball is low, so it will simply float. But because it is dropped from some height, it is having some velocity, so because of that momentum, it will enter into the liquid. And once it is entered, now upward will be buoyancy force, downward will be its weight, and you can see because density is low, so this weight will be low and this will be high, so ball will have net upward acceleration. So if I say, let's say volume of ball is v, then let me calculate its upward acceleration. So I can write net force F net is equal to mass into acceleration. F net is equal to how much? Buoyancy force minus mg equal to m into a. How much is buoyancy force? Buoyancy force will be equal to v is the volume multiplied by density of liquid into g minus mass v into density 0.8 into g. This mass volume multiplied by 0.8 multiplied by acceleration a. So not sorry, g is not cancelling, v cancelled out, and this is g. 10 minus 8, this will be equal to 2, that is equal to a like 0.8 into a. So this solving a, I am getting basically 10 by 4, that is g by 4 is the acceleration, and this is upward. So finally it's asking how much ball, like how much like it will sink, ball will sink. So means finally when it is at the highest point or highest depth, final velocity will become here, v final will be 0, initial velocity root 40, and it's like constant acceleration motion. So we can apply third equation. So v final square minus u square is equal to 2 into a into s, and this is equal to 0 minus this will be 40 minus 2 into g by 4 into s. Solving it, this is 2 10 10 and s is coming out to be 8 meter. This is answer to this problem. So I hope you are clear with this. Again, why it is sinking, and finally we understood here acceleration, final velocity will be 0. Using third equation we are getting the depth at which the velocity will become 0, and from there the ball will bounce back. So that will be the maximum sink, or the maximum depth up to which ball will sink. So this is all some problem based on Archimedes principle, and let's see next. Okay, so see next problem. So here when a polar bear jump onto an iceberg, its weight of polar bear 200 kg weight is just sufficient to sink the iceberg. Then weight of iceberg is, specific gravity of ice is given, and specific gravity of water is like seawater is this. Then based on it we can write density of ice will be this, density of water is this. Okay, so let me first tell you the problem, what exactly is happening here. So let's say this is the sea level, and there is some iceberg, so like this, and this is your iceberg actually, right? Now what is happening, if it's, let's say v is the total volume of ice, then we know actually, because density of ice is less than density of water, so that's why it doesn't like means ice float on the water with some part like still staying outside. So you can see actually this will much, this is the v outside and this is v inside sinked, or v outside can be v minus v inside, total volume, right? And now what it's saying is that when a polar bear is jumping on it, of weight how much, 200 kg. So when let's say this polar bear is jumping on it, then what is happening, this ice means this is almost sinking completely like this. So what it means, its polar bear weight is 200 kg. So it's still like polar bear is outside, but this ice is almost like completely sinked. What it means, this additional volume has went into water, so means it has displaced a additional water of v minus vi, and weight of this displaced water will be multiplied by density into this weight is sufficient to the weight of polar bear, right? So by using that relation I will get total volume of this iceberg. Once we have total volume of iceberg, then I will multiply that with the density of ice, we will get mass of ice, and weight of ice will be simply multiplied by g. So this is the problem, means initially let's say total so this is the condition. So let total volume of ice, total volume of iceberg is, I will say, V. Clear? Then Vi is this is immersed volume. Then what you can write, I like, so once polar bear jumping on it completely, so let me first get how much is V or Vi. So we know actually Vi, volume immersed divided by total volume, will be equal to density of ice divided by density of water. If I just do some small mathematics, 1 minus this, 1 minus this, then it will be equal to how much? V minus Vi divided by V equal to rho water minus rho ice divided by rho water. This is the volume staying outside. So that can be written as V minus Vi is equal to rho water minus rho ice divided by rho water multiplied by total volume. So we got one relation. Clear? Now what is happening? So weight of displaced water of volume V minus Vi is balancing the weight of polar bear, right? I hope this sentence should make sense to everyone. So now I can use this condition. So this weight of polar bear is 200 into G, and this should be equal to weight of displaced volume of water, that is equal to V minus Vi multiplied by density of water into G. Clear? So this G cancelled. V minus Vi, I can substitute it this. So this is equal to rho water minus rho ice divided by rho water multiplied by total volume into density of water into I like G, I already cancelled. So this cancelled. Now what total volume of ice is coming out to be 200 divided by rho water minus rho ice. So this is the total volume of iceberg. Clear? The question it's asking is the iceberg, then the weight of iceberg is. So weight of iceberg means I can calculate mass of iceberg. So that will be equal to how much? Volume into density of ice, that is equal to 200 divided by density 1020 minus 900 multiplied by 900. This comes out to be 200 into 900 divided by 120. 10 gone, this 3, so 30, this is 4, and this is how much? 5. 50 into 30, that comes out to be 1500 kg. So this is the mass of iceberg. Weight of iceberg will be equal to 1500 kg weight. So this is the problem. I hope you understood. Initially iceberg was floating with this much volume outside and Vi is inside. Polar bear jumping, then polar bear is still in the air, like it's still like not submerged, but the remaining part which was earlier floating of ice is also now submerged. So the weight of polar bear is balanced by this submerged volume of ice. So that way we are getting total volume of ice, and then total mass of the ice is volume multiplied by density, and solving we are getting this problem. And so weight of the total iceberg or mass is coming out to be 1500 kg. Weight will be 1500 kg weight. This is about this problem.